Okay, I want to try something a little different today. I want you to stop what you're doing for just a second. If you're driving, obviously keep your eyes on the road. But if you're safe to do so, I want you to close your eyes.
All right, I'm closing mine. I'm trusting you not to lead me into a wall here.
No walls, I promise. Now reach out and touch the table in front of you. Or the arm of your chair, maybe the fabric of your jeans. Just run your fingers over it.
Okay.
Really pay attention. Is it cool? Is it rough? Is it smooth?
Okay, I've got the arm of my chair. It's that cheap office mesh stuff, so yeah, rough, a little cold.
Okay, open your eyes. Now here is the question that is going to absolutely haunt us for the next hour or so. Did you actually touch that chair?
See, this is a trick question. Functionally, in your day-to-day life, yes, of course you touched the chair. But if we are being physiologically accurate, if we are looking at the raw mechanics of biology,
Then no.
no,
Yeah.
absolutely did not.
This is the part that just breaks my brain every time I think about it. This is the reality interface. Because what actually happened just now isn't that your finger touched a chair.
Right.
What happened is that you experienced a series of electrical signals in a pitch black, silent room.
That room being your brain.
Exactly. And we need to sit with that image for a second. Your brain, it has never seen a sunset. It has never tasted a strawberry. It has never felt the warmth of a fire.
Not directly.
It is locked inside a bone vault, your skull floating in cerebrospinal fluid,
Yeah.
in total absolute darkness.
It's true. The brain is completely isolated from the universe.
Yeah.
The only thing it knows about the outside world comes from these tiny biological telegrams being sent up the wires.
The wires being the nerves.
Right. It's constructing a simulation based on coded data.
It's like a pilot flying a plane with the windows blacked out, flying purely on instruments.
That is a perfect analogy.
Yeah.
And today, we're stripping down the dashboard. We are looking at the instruments themselves.
We're doing a deep dive into the hardware of that interface.
We are breaking down Chapter 47. Sensory receptors, neuronal circuits for processing information.
Our mission today is seemingly simple, but when you peel back the layers, it's scientifically incredibly complex. We want to trace the journey of that touch.
The whole thing, from start to finish.
From the moment the physical atoms of the chair deformed your skin, to how we turn that physical pressure into electricity, send it up a wire, and figure out how the brain processes that data without blowing a fuse.
And blowing a fuse is a literal risk here, as we will see later. The brain is an electrical machine that has to constantly stop itself from short-circuiting.
So let's unpack this. If the brain is locked in the dark, it needs translators. It needs, agents in the field to tell it what's going on.
Those are your sensory receptors. The source material categorizes them into 5 basic types. Think of these as the 5 translators that speak the languages of the universe.
And they translate it all into the one language the brain understands.
Which is just electricity.
It's all just voltage.
Precisely. The brain speaks voltage. That's it. So first up, you have mechanoreceptors.
Okay, so these are the ones dealing with mechanics. Pushing, pulling, that kind of thing.
Right, compression and stretching. This is touch, obviously, but it's also your eardrums vibrating from sound waves. It's even the sensors in your arteries detecting blood pressure changes.
So it's not just external touch.
Not at all. It's all just stuff moving stuff.
Okay, what's number 2?
Number 2, thermoreceptors.
Easy enough. Heat.
These detect changes in temperature. And interestingly, as we'll see, we have different sensors for cold and warm. They aren't the same thermometer.
Well, that's interesting. Okay, number 3, the one nobody likes, but we'd be dead without it. Nociceptors.
Pain receptors. Noci is from the Latin for harm. So these are the damage control team. They detect physical damage, chemical burns, crushing trauma. They are the alarm system.
The big red button.
The biggest.
4th, we have electromagnetic receptors. This sounds like something out of a sci-fi movie, but it's just vision, right?
It is. It's light hitting the retina. But think about what that is. It's detecting electromagnetic radiation from the sun or a lamp. It's literally capturing photons.
Yeah, you don't think about it that way. And finally, number 5.
Chemoreceptors.
So, chemistry.
These are detecting the chemistry of reality. Taste and smell are the obvious ones, detecting chemicals in food or air, but also internal chemistry. Oxygen levels in the blood, carbon dioxide concentrations, the osmolality of your fluids.
So half of them are sort of looking outward and half are looking inward.
A good way to put it.
Now, here's where it gets really interesting to me. We have these 5 types. But how do they stay in their lanes? Why doesn't my eye taste the light? Or why doesn't my finger hear the table?
That is the principle of differential sensitivity. It's a crucial concept in the text. Each type of receptor is designed to be hypersensitive to one specific type of stimulus and practically blind to everything else.
So the rods and cones in my eye are just ridiculously sensitive to photons.
To a single photon in some cases. But you could blast them with heat or pressure or sound waves, and they wouldn't register a thing.
Really? Like if I push on my eye, I see stars when I do that?
Well, there is a caveat. If the pressure is so extreme it causes damage, or it's enough to mechanically stimulate them in a weird way, you might see stars. But generally, they are tuned to a specific frequency of reality. They're not pressure sensors.
Okay, so the sensor is specialized. My eye is the camera, my ear is a microphone. But this leads us to a massive mystery. This is section 1 in our breakdown, the labeled line principle.
This is the big one.
Because, okay, the sensor is different, but the wire, the nerve fiber, isn't that just sending the same generic electrical pulse?
That is the core mystery of neuroscience. If you look at an electrical impulse on an oscilloscope, if you look at the spark from a pain nerve and the spark from an optic nerve,
You're identical.
they look identical. It's just an action potential. It's just a spike of voltage.
So if the signal is identical, how on earth does the brain know that one is a flash of light and the other is a pinprick?
It's not the message, it's the mailbox.
The mailbox, what do you mean?
Think of it this way, it's the labeled line. The brain knows what you're experiencing, not by how the signal travels, but by where it ends up in the brain.
Can we break that down?
Sure. The text uses the example of a pain fiber. If you stimulate a pain fiber, the brain perceives pain. It doesn't matter how you stimulate it.
So it could be a cut.
You could crush the nerve, you could burn it, or, and this is key, you could zap it with electricity.
Wait, hold on. If I zap a pain nerve with electricity, the brain doesn't say, hey, that was a volt of electricity.
No, it says, ouch. Because that wire is plugged into the pain center of the brain. The brain assumes that any signal coming down that specific wire must be pain. The line is labeled pain.
Wow. So if I could somehow unplug my optic nerve, the eye wire, and plug it into the hearing center of my brain, and then I looked at a sunset,
You would hear the sunset. You would experience it as some kind of sound.
that is tripping me out.
It should. It suggests that our entire sensory experience is, in a way, arbitrary based on the wiring. And we see this in the real world. Have you heard of the phantom limb phenomenon?
Yeah, that's when someone loses an arm or a leg, but they still feel it, right? Like it itches?
Exactly. And the labeled line principle explains why. Let's say you have a nerve fiber that starts in your big toe and runs all the way up your leg to the brain. That line is labeled big toe.
Okay, simple enough.
Now, unfortunately, the leg is amputated at the knee. The toe is gone. The sensor is gone. But the wire, the nerve fiber, is still there, running from the knee to the brain.
I see where this is going.
If that cut nerve at the stump gets irritated, maybe by scar tissue or inflammation, just a random firing, it sends a signal. That signal travels up the same old line to the brain.
And the brain gets a signal in the big toe mailbox.
Right. Because it's in a dark room, it has no way of knowing the toe is gone. It just checks the label on the wire and says, oh, the big toe itches.
And to the person, that itch is 100% real.
Exactly. To the brain, the toe is just as real as it ever was because the signal is arriving on the big toe line. Reality is just which wire gets buzzed.
It really reinforces that we are just interpreting signals. We aren't experiencing the world. We are experiencing our own switchboard.
It really is. And if you cross those wires, which happens in a condition called synesthesia, people report tasting colors or seeing sounds.
So their labeled lines are getting delivered to the wrong processing center.
That's the theory. The grape signal from the tongue gets routed to the visual cortex by mistake, and suddenly the taste has a shape.
Okay, so we have the translators and we have the labeled lines carrying the data, but let's zoom in, like electron microscope level. I want to know what happens at the very, very tip of that nerve.
The point of contact.
Yeah. How do we turn a physical push actual kinetic energy into an electrical spark?
This is the process of transduction. And this is where we have to get into the nitty-gritty of the chemistry. Regardless of whether it's touch, light, or heat, the goal is the same. Create a receptor potential.
Which is basically a change in the voltage of the membrane, right? But walk me through the physics of it.
Okay. Imagine a nerve fiber. It's a long tube. It has a skin called the membrane. Now, in its resting state, the inside of that tube is negatively charged compared to the outside.
Right, it's polarized.
Exactly. It's like a little battery waiting to be used.
Okay, negative inside, positive outside.
And the reason it's positive outside is because there is a massive crowd of sodium ions waiting there.
Sodium. It's always sodium in these textbooks. It's the main character.
Sodium is the star of the show. Think of sodium ions as a crowd of people at a concert pressing against the gates. They are positively charged. They are desperate to get inside the club, the nerve fiber, because it's negative inside, and opposites attract.
And there are way more of them outside than inside, right?
Exactly. There's a huge concentration gradient pushing them. They're banging on the door
Just so they want in badly.
desperately, but the doors are locked. The membrane is impermeable to sodium in its resting state.
So transduction is just unlocking the door.
That's it. That's the whole game. When we say transduction, what we really mean is opening a hole in the membrane so sodium can rush in.
And the text says there are 4 ways to pick that lock, right?
Correct. 1, mechanical deformation. You physically stretch the membrane. Imagine grabbing the gates and pulling them apart until they break open. That's what happens when you touch something.
Okay, that's physical force. What's 2?
2, chemical application. A chemical floats over, acts like a key, puts itself in the lock, and opens the door. That's smell and taste.
Got it, like a little molecule key.
3, temperature change. Heat actually changes the permeability of the membrane. It makes the gates looser, effectively letting ions leak through.
Right.
And 4, electromagnetic radiation, which changes the membrane characteristics directly in the retina.
So in all these cases, the result is the same. The gates open.
And the sodium mob rushes in.
And because sodium is positive, when it rushes in, it neutralizes that negative charge inside. The voltage shoots up. The inside becomes positive.
And that rising voltage is the receptor potential.
Now, the text actually gives us a really deep dive into a specific case study for this to help us visualize it. The Pacinian corpuscle.
The big one for touch.
This is the main touch sensor, right?
Yes, this is the classic example of a mechanoreceptor. If you look at the diagram in the source, figure 47-3, it looks remarkably like an onion.
It really does. It has these concentric layers, and right in the middle, buried deep like the core of the onion, is the central nerve fiber.
So imagine you press on that onion. The compression goes through the layers and physically forms that central fiber. It bends it. It squishes it.
And that bending is what opens the sodium gate.
Exactly. The membrane stretches, the sodium channels pop open, and the sodium ions flood into the tip of the fiber. This creates that pocket of positive charge. But, and this is a critical distinction that often trips people up, this receptor potential is not the signal that goes to the brain yet.
Wait, what? We just went through all that trouble to get the sodium in. Why isn't that the signal? I thought voltage was the signal.
Because that electrical change is local. It's just a spark at the tip. It's what's called a graded potential. It hasn't started the fire that travels all the way up the wire.
Okay, so it's not the main event. How does the spark become the fire?
This initial change in voltage induces a local circuit of current flow. The positive charge inside pushes other positive ions down the fiber, and that current flows along the fiber inside the capsule until it hits the first node of Ranvier.
The node of Ranvier? I love that name. It sounds like a location in Lord of the Rings. You cannot pass the node of Ranvier.
It does have a fantasy vibe, but physiologically it's just the first gap in the insulation. See, the nerve fiber is insulated with myelin. Think of it as rubber coating on a wire, but the myelin doesn't start until outside the capsule.
So there's a little bit of bare wire inside the onion.
Precisely. So the electrical current has to flow from the tip through that uninsulated part until it hits that first spot where the insulation starts. That's the node.
And that's where the magic happens.
That is where the magic happens. The local current reaches that node, depolarizes the membrane there, and that is what triggers the actual action potential.
So the receptor potential is like lighting the fuse, but the action potential is the dynamite exploding.
Exactly. The action potential is self-propagating. Once it starts at the node of Ranvier, it shoots all the way to the brain without losing strength. But it requires that initial local push to get started. I see. So the capsule is just the mechanical trigger mechanism. The node of Ranvier is the firing pin.
That's a great analogy.
Now, I want to talk about amplitude and intensity, because a touch can be a feather or it can be a hammer. If the action potential is just a bang, an all-or-nothing event, how does the nerve tell the brain the difference? Does the voltage just get higher and higher?
This is where people get confused. The answer is yes and no. The source material talks about a 100 millivolt ceiling.
A ceiling, like a maximum voltage.
Right. Think back to our sodium crowd. As the stimulus gets stronger, you press harder and harder. The mechanical deformation opens more and more gates. Sodium rushes in faster. So the receptor potential gets bigger.
The receptor potential voltage rises. But eventually, the membrane is wide open. Every single sodium door is open. The sodium is flowing as fast as physics allows. You can't get any more open.
There's a bottleneck.
A sodium bottleneck. So the voltage maxes out at about 100 millivolts.
So if the voltage caps out, how do I know the difference between a hard pinch and a really, really bone-crushing pinch? If the voltage is the same, shouldn't it feel the same?
Frequency translation. This is the beauty of the system. The brain doesn't look at the amplitude of the action potentials arriving. It looks at the rate of fire.
Morse code.
Exactly. But it's Morse code where the urgency is in the speed. The higher that receptor potential rises above the threshold for firing, the faster the action potentials fire one after another.
So a weak touch is like dot, pop, pop,
Pop.
pop, pop,
And a strong touch is
pop, 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 pop.
it translates voltage amplitude into frequency.
So the brain is just counting clicks per second. That's the code for intensity.
That's it. A few clicks per second. Someone is brushing your arm. 1,000 clicks per second. A truck just ran over your foot.
Now, speaking of urgency, have you ever noticed that when you first put on a shirt, you feel the fabric on your skin? It's cool, it's maybe a little scratchy,
Oh, yeah.
but 30 seconds later, you don't feel it at all.
All the time. Or wearing a watch. Or glasses. You forget they are there until you think about them, and then suddenly you feel them again.
That is section 3, adaptation, getting used to it.
It's a vital function. Imagine if your brain had to constantly process the sensation of your clothes, your watch, your glasses, the pressure of your butt on the chair, the air conditioning blowing on your arm.
It would be a nightmare. It would be total information overload.
Exactly. The brain needs to filter out the status quo so it can focus on changes. If a tiger jumps at you, you need to feel that, not the tag on your underwear.
So how does that happen? Is the brain just ignoring the signal? Is there a spam filter in the brain?
Actually, the adaptation happens right at the receptor level. The signal stops being sent entirely.
Oh, wow. So the nerve just gives up.
It does. And the text outlines 2 distinct mechanisms for this, specifically in that Pacinian corpuscle we talked about.
Okay, let's break them down. Fast versus slow.
The fast mechanism is purely mechanical. It's called viscoelastic adjustment. Remember the onion layers and the fluid between them.
Yeah, the squishy interior.
When you first press down, the fluid transmits that pressure to the center core. It squeezes the nerve. Signal fires.
Okay, that makes sense.
But within a fraction of a second, the fluid redistributes. It flows away from the pressure point. It's viscous, so it moves.
Wait, like a waterbed? Or one of those gel stress balls?
Exactly like a waterbed. You sit down on a waterbed, and for a second there is pressure. But then the water displaces to the side, and the pressure point diffuses. So even though your finger is still physically pressing down on the outside of the capsule, the pressure on the inner core vanishes.
That is incredibly clever. The structure itself is designed to hide the signal from a constant stimulus.
It is. So the receptor potential disappears, and the signal stops. That happens almost instantly. But there is a second, slower mechanism called electrical accommodation.
The nerve gets bored.
Basically, even if the core was still being distorted, let's say the water didn't move, the nerve fiber itself changes. The sodium channels effectively inactivate.
They close up shop, like they just jam themselves shut.
They do. It's a conformational change in the protein. It's like the door requires a fresh knock to open again. Leaning on the doorbell won't keep it ringing. The nerve adjusts its own chemistry to say, I've seen this sodium level. I'm not impressed anymore.
This leads to a distinction the text makes between tonic and phasic receptors, or as I like to call them, the tortoise and the hare.
Good analogy. Let's start with the tortoises, the tonic receptors. These are slowly adapting.
These are the ones that don't give up. They just keep firing for hours if they have to.
Right. Muscle spindles, the Golgi tendon apparatus, pain receptors, and the chemoreceptors in your carotid artery monitoring your blood chemistry.
Why do we need these to stay on? Why don't they adapt like the shirt sensor?
Because you need to know the status quo for survival. Your brain needs to know exactly how contracted your bicep is right now to hold that coffee cup.
Right.
If that receptor adapted and stopped firing, your brain would think the arm was relaxed and you'd drop the cup.
Or pain. If I broke my leg, I wouldn't want my brain to get used to it and stop telling me not to walk on it.
Exactly. Pain needs to be persistent so you protect the injury. You need continuous tonic data.
Okay, it makes sense. So those are the tortoises and the hares, the phasic receptor.
These are rapidly adapting, or rate receptors. The Pacinian corpuscle is the prime example here. They only fire when the stimulus changes.
So they don't tell you there is pressure. They tell you pressure is increasing or pressure is decreasing.
Precisely. They detect the rate of change.
Yeah.
And the text gives a fascinating example of why this matters so much. running around a curve.
Oh, this was the predictive function part. I love this. It sounded like the brain is a time traveler.
It effectively is. Think about the physics of running. If you are sprinting and you turn a sharp corner, you are unstable. Centrifugal force is trying to throw you over.
Right, you have to lean into the turn.
Now, if your brain waited for you to actually start falling to correct your balance, it would be too late. Gravity's fast. By the time the signal got to your muscles, you'd be face planting.
So what does the rate receptor do? How does it help?
The vestibular receptors in your ear are rate receptors. They detect the speed of your turning head. They don't just say, we are turning. They say, we are turning at 15 degrees per second and accelerating.
And the brain does math with that, like it calculates the trajectory.
In nanoseconds. It extrapolates the curve. It predicts where your legs need to be 2 seconds from now to counteract the force that hasn't even happened yet. It's predictive control.
That is wild. So without these rate receptors, we'd always be reacting to the past.
Exactly. You'd always be lagging behind reality. Rate receptors allow the brain to project into the future. It allows you to run, catch a ball, or even walk without toppling over.
It's a beautiful biological algorithm. If X equals speed, move leg to Y.
And it happens without you ever thinking about it. Purely subconscious.
All right, so we've generated the signal, we've encoded it with frequency, we've filtered it for change. Now we have to ship it. We're on to section 4, the cables, nerve fiber classification.
Highway system of the body. And just like highways, there are speed limits.
The text mentions a massive range here. We're talking about signals moving at 120 meters per second all the way down to 0.5 meters per second.
Let's put that in context.
Yeah.
120 meters per second is like a race car. That's over 260 miles per hour. That is basically instant communication within the scale of the human body.
And 0.5 meters per second.
That's a slow walk. I could walk faster than that signal travels. It takes 2 full seconds for a signal to go from your foot to your head. It's agonizingly slow.
Why the difference? I mean, if we have the technology for Ferrari nerves, why do we have so many tractor nerves? Why isn't everything fast?
Because speed is expensive, biologically expensive. To get that speed, you need thick nerve fibers, and you need heavy insulation myelin. That takes up physical space in the nerve bundles, and it consumes metabolic energy to maintain.
So it's a resource issue.
It is. You don't need a Ferrari to deliver the mail. You save the high-speed lines for the information that is truly life or death.
So how are they classified? The text breaks them down into type A and type C.
Type A are the Ferraris. They are myelinated, large, fast. They are subdivided into alpha, beta, gamma, and delta based on size and speed.
And what do we use these for? The important stuff.
Precise, time-critical info, muscle control. If you trip, your muscles need to react now to catch you. That needs to be on the alpha line. Or sharp touch, knowing exactly where a pin pricked you.
Okay. And the type C fibers.
The tractors. Unmyelinated, small, slow, but, and this is a big but, they make up more than half of all sensory fibers in most peripheral nerves.
So the majority of our bandwidth is slow. That seems backward.
It is. This is for aching pain, crude touch, temperature, tickle, itch. Things that don't require split-second reactions. You don't need to know the exact location of an itch with millimeter precision instantly.
That explains the double pain phenomenon, right? I stubbed my toe the other day, badly, and I noticed this distinct delay.
Walk us through it. What did you feel?
Okay, so I kicked the table leg. Bam! There was an instant, sharp, electric shock of pain. It made me gasp.
That is the type A delta fiber. Fast, myelinated, telling you damage has occurred at location X. It's the warning shot. It's the pull your foot back now signal.
But then there was this weird pause, like a full second or two, where I thought, oh, that wasn't so bad. And
The
then,
wave hits.
oh man, the throb, the dull, aching, sickening pain that just rolled over my foot and lasted for 10 minutes. It was almost a different sensation entirely.
That is the type C fiber finally arriving with the bad news. It's the slow, unmyelinated tractor chugging up the spinal cord carrying the chemical payload of misery.
It's like the type A is the text message. You hit her toe. And the type C is the certified letter that arrives a week later saying, Dear Sir, regarding the toe incident, we are writing to inform you that the tissue is inflamed and will remain so for the foreseeable future.
A perfect analogy. And biologically, that type C pain is meant to make you immobile. The sharp pain makes you pull away. The dull pain makes you sit down and rest so it can heal. They have different jobs.
So we've got these signals racing or crawling up the spinal cord. But here's a problem I see. How does the brain know if a signal is intense? We talked about frequency earlier, the Morse code clicking faster. But is there another way? This is section 5, signal processing.
Intensity and summation. Yes, we have two main ways to scream "this is important" to the brain. We touched on one, but let's formalize them. Solution A is spatial summation.
Spatial meaning space, like over an area.
Right. The text uses the pinprick diagram, figure 47-7. Imagine a weak poke with a needle. It might only deform the skin enough to trigger a single nerve ending in the center of the field.
So one wire is firing, the brain gets one signal.
But if you poke harder, you deform a larger area of skin. You recruit the neighbors. You start triggering the nerve fibers surrounding that central point. So now the brain isn't just hearing one voice, it's hearing a chorus.
It's hearing from multiple locations at once, saying, we are all feeling this.
Exactly. The more fibers recruited, the stronger the perceived intensity. That is spatial summation. It sums up the signal over a larger space.
Okay, that makes a lot of sense. And solution B?
Temporal summation. This goes back to our frequency discussion. Temporal means time. It's the same single fiber, just shouting faster, increasing the frequency of impulses over time.
So let me see if I have this. Spatial is more people yelling. Temporal is one person yelling louder and faster.
Correct. And the brain combines both to gauge reality. If you have a lot of fibers firing very, very fast, the brain knows this is a major event.
Moving on to section 6. We are leaving the individual nerve now and entering the wiring diagram. Neuronal pools.
This is where things get really complex. We are no longer talking about a single wire. We're talking about how these wires connect to the computers, to the processing units.
A neuronal pool. It sounds relaxing. I imagine a spa for neurons.
It's anything but a spa. It's a chaotic intersection of information. The cerebral cortex is a massive pool. The basal ganglia is a pool. The entire gray matter of the spinal cord is a pool. Think of it more like a busy stock exchange floor or a massive data center.
So you have an input fiber coming in. It doesn't just touch one neuron, right? It's not a one-to-one connection.
No, not at all. It branches out like a tree, connecting to thousands of output neurons. And this introduces the concept of the field. The field is the area of neurons that one input fiber can influence.
But influence doesn't always mean fire, right? Just because I touch a neuron doesn't mean it goes off.
Correct. And this brings us to the threshold concept. This is crucial for understanding how we think and react. Imagine an input fiber comes into the pool. The neurons directly in the center of its field, where it has the most connections, receive a massive blast of neurotransmitters.
They get the full dose. They're right in the blast zone.
Right. They hit the threshold immediately and fire. That's the discharge zone, or liminal zone.
Okay, straightforward. They get enough signal, they fire.
But the neurons on the edges of the field, they get a little signal. Maybe they have fewer connections, they get some neurotransmitter, but not enough to pull the trigger. They don't fire.
So they are useless. They just sit there.
Not at all. They are in the facilitated zone, or subliminal zone. They are primed. They are on the edge of their seats.
Explain that. What does primed mean in a neuron? What's happening chemically?
It means their membrane potential has risen slightly. Let's say the resting potential is ending at 70 millivolts, and the firing threshold is -55. A facilitated neuron might be sitting at 80 to 60.
So it's closer to the firing threshold than normal. It's easier to excite.
Much easier. So now a second signal from a completely different input fiber comes along. On its own, that second signal is also too weak to make a neuron fire. But when it hits that already facilitated neuron,
It pushes it over the edge.
it's enough. That's how the brain integrates information from multiple sources. It's not just on or off. There's this middle ground of almost on.
That is fascinating. So the pool is constantly shifting its sensitivity based on what's going on.
Constantly. Now let's talk about how the signal spreads. Divergence?
Divergence is taking one signal and spreading it to many. The text lists two types.
First, the amplifying type. One signal in, 10,000 out.
The text gives the example of the motor cortex.
Right. You have one pyramidal cell in your brain that decides move the leg. That is a single command from a single neuron. But your leg is huge. It has thousands of muscle fibers.
So the signal hits a pool in the spinal cord and explodes.
It diverges. That one signal triggers a cascade that eventually fires 10,000 muscle fibers. It amplifies the command so a tiny thought can lift a heavy weight.
And the second type of divergence.
Divergence into multiple tracks. This is about multitasking. A sensory signal comes up the spinal cord. It diverges.
Where does it go? It splits off.
It splits. One branch goes up to the sensory cortex, so you can consciously say, I feel pain in my foot. But another branch goes to the cerebellum to help you adjust your balance because you just stepped on something sharp.
So one input serves different purposes in different parts of the brain simultaneously.
It's like sending a group email. CC. Cerebellum, CC thalamus, CC cortex.
Exact.
Then we have the reverse,
Convergence.
focusing the signal. Multiple inputs connecting to a single output neuron. Why would we want that? That sounds like a bottleneck.
It's not a bottleneck. It's a committee meeting. It's about making decisions. Think about an interneuron in your spinal cord. It's trying to decide whether to fire a motor neuron to move your hand.
Okay, it's got a choice to make.
It receives input from your skin, peripheral nerves, saying, whatever we are touching is hot. It receives input from your brain, corticospinal fibers, saying, but we need to hold this coffee cup, don't drop it. It receives input from other spinal segments about your arm's position.
So it has conflicting info. One says drop, one says hold. It takes all those votes, some excitatory, some inhibitory, sums them up, and makes a single decision.
Yeah.
Fire or don't fire. Drop the cup or hold it.
So convergence is the mechanism of choice. It averages the data to produce a coherent output.
Exactly. It's how you can do complex tasks.
There's one more circuit type in this section that I found really clever. Reciprocal inhibition. The walking circuit.
This is essential for any coordinated movement. I want everyone listening to try this. Flex your bicep. Make a muscle.
Okay, flexing.
When you flex your bicep, your tricep, the muscle on the back of your arm must relax. If both contracted at the same time, your arm would just lock up straight. You wouldn't be able to bend it.
Right. They're opposing forces. They're an antagonistic pair.
So how does the brain handle that? Does it send two separate signals? Flex bicep and relax tricep.
That seems inefficient. You might get the timing wrong.
It is. Instead, it uses reciprocal inhibition. The input signal from the brain excites the motor neurons for the flexor muscle, but simultaneously that same wire branches off and hits an inhibitory interneuron.
An inverter. A not gate.
Right. That inhibitory neuron sends a shut-up signal to the motor neurons of the extensor muscle. So the harder you flex the bicep, the more you inhibit the tricep.
It turns off the opposition automatically. It's built into the circuit.
It's hardwired. You don't have to think about it. It makes movement smooth and possible.
Okay, we've moved the signal, processed it, and made a decision. But sometimes a thought lingers, or a reaction lasts longer than the touch. This is section 7, memory and rhythm.
Prolonging the signal. This is after discharge. The input stops, but the output keeps going for a little while.
How? Is it like an echo?
The simple way is synaptic after discharge. The neurotransmitter chemical just hangs around at the synapse for a few milliseconds. It hasn't been cleaned up yet by enzymes, so it keeps triggering the next nerve.
But that's only milliseconds. What about seconds or minutes? Or a thought that stays in my head all day?
For that, we need a reverberatory circuit or an oscillatory circuit. This is positive feedback.
The echo chamber.
It really is. Imagine neuron A fires and triggers neuron B. But neuron B has a collateral wire as side road that goes back and triggers neuron A again.
A creates B. B recreates A. A recreates B.
And round it goes. The signal circles and re-excites itself. This can keep a signal alive for seconds or minutes after the initial stimulus is long gone.
This is short-term memory, isn't it? Like holding a phone number in your head?
It's the physiological basis of it. It's a holding pattern for data. You're literally keeping that pattern of firing alive by making it loop.
But wait, if it's a loop, wouldn't it just stay the same? The text mentions rhythmical signals like breathing. How does a loop create a rhythm? That seems different.
This is one of my favorite parts. Breathing isn't a switch that goes on-off. It's a reverberating circuit in your medulla and pons.
How does that work?
The signal starts weak. It enters the loop. It amplifies. It reverberates, getting stronger and stronger as it recruits more neurons in the pool. This is the ramp signal.
So as you inhale, the signal's actually growing.
Yes. You inhale, and the signal recruits more and more neurons. The diaphragm pulls harder and harder, giving you that smooth intake of breath.
And then...
What stops it? And then inhibitory signals, or just plain old fatigue in the circuit, cut it off. The loop breaks. You exhale passively. Silence. And then the spontaneous excitability of the neurons starts the loop all over again.
The text also mentions a carrier wave. This concept blew my mind. The brain has a dial tone.
Yes. Many neuronal pools are never silent. They have a spontaneous excitability. Their membranes are just naturally leaky enough that they are constantly firing at a baseline rate.
A hum. A constant hum of activity.
A hum. Think about a radio carrier wave. If the line was silent, you could only turn it on. That's one bit of information. But if it's already humming, you can turn it up, excitation, or turn it down, inhibition.
So you get two directions of information flow on the same wire.
A much richer data stream. So silence isn't the baseline. Activity is the baseline. Your brain is never truly quiet.
But this brings us to the danger zone. Section 8, stability. Because if we have all these amplifiers and all these positive feedback loops where A triggers B triggers A, and we have spontaneous excitability,
I see where you're going with this.
why doesn't the brain just explode? Why doesn't one spark set off a forest fire that consumes the whole cortex?
That is the ultimate question of brain function. Why don't we all just go into massive seizures instantly? Because that's what a seizure is. It's uncontrolled reverberation. The signal breaks containment and takes over the whole brain.
So how do we stop it? What are the brakes?
We have three major safety valves. Mechanism 1, inhibitory circuits. We talked about these briefly for movement. But on a macro level, you have entire regions of the brain, like the basal ganglia, whose main job is just to send stop-it signals all over the place.
To the fun, please.
They're the dampeners. They suppress muscle tone and unwanted activity. If they fail, like in Parkinson's disease, you get rigidity and tremors. The brakes are cut.
Okay, so inhibitory circuits. What's mechanism 2?
Mechanism 2 is something we've all felt. Fatigue.
Synaptic fatigue. And in the brain, fatigue is a feature, not a flaw.
Explain that. Usually fatigue is bad.
Not here. Synapses run on chemicals, neurotransmitters. Every time a neuron fires, it spits out a little packet of this chemical, but it only has a limited supply stored at the tip. Like a gun with a magazine. You only have so many bullets.
Exactly. If a circuit fires too fast for too long, like in a seizure or a runaway reverberating loop, it literally runs out of ammo. It runs out of transmitter substance faster than it can recycle or create it.
So the signal gets weaker and weaker with each shot.
Yes. The text details the flexor reflex example. Yeah. If you stimulate a reflex over and over, the muscle contraction gets weaker and weaker. The synapse is tired.
And this stops a seizure?
It's a failsafe. If a reverberating circuit spins out of control, eventually the synapse is fatigued, the signal degrades, and the loop breaks. It's often why a grand mal seizure ends. The brain literally exhausts itself. It runs out of chemistry.
That brings us to mechanism 3, and this is a long game. This isn't second by second, this is upregulation and downregulation.
This is how the brain maintains stability over days and months. It's the math of the brain, as the text calls it. It's constantly auto-calibrating.
So if a circuit is too quiet, if it's not getting enough input,
If a circuit is underused, the synapse says, hey, I'm missing the signal. It's too quiet in here. It physically synthesizes more receptor proteins and installs them on the membrane.
it adds more ears. It's trying to hear better.
It becomes hypersensitive. It turns up the volume. This is upregulation.
And if it's too loud, like from chronic overstimulation,
If a circuit is overused, maybe by drugs or loud noise or chronic pain, the synapse removes receptor proteins. It inactivates them or pulls them inside the cell. It turns the volume down. That's downregulation.
so the brain is constantly adjusting every single neuronal pool to keep it in the Goldilocks zone. Not too quiet, not too loud.
That is incredible. It's self-tuning hardware. There's no engineer doing it. It just happens.
It is, but, and here is where we get to the outro, that self-tuning can be a problem. It can go wrong.
I think I know where you are going with this, the dark side of upregulation.
You mentioned that if a circuit is underused, the brain upregulates it and makes it hypersensitive to try and find a signal.
Right. It's looking for input.
The text mentions that this can lead to muscle cramps in denervated muscles, but it also mentions something else, psychotic disturbances and hallucinations.
This is the dark side of the dark room.
Let's talk about sensory deprivation. If I lock a person in a soundproof, pitch-black room for a week, what happens to their brain?
Their sensory circuits are bored. Their auditory cortex, their visual cortex, they're getting zero input. So following the rules of stability, they upregulate. They crank the sensitivity to maximum.
They are desperate for a signal, any signal.
They are. And when you turn the gain up that high on a microphone, what happens?
You get feedback, static. You hear the hum of the electronics.
Exactly. The brain starts picking up the random thermal noise of the neurons themselves. It starts interpreting its own spontaneous firing as reality. It starts hearing voices where there is only silence. It starts seeing ghosts in the darkness.
That is actually horrifying. You're telling me the ghosts people see in isolation, the voices they hear, are just their brain turning up the volume because it's lonely.
Your brain hates the silence.
Yeah.
It is a pattern-matching machine. If you don't give it a pattern, it will create one from the noise. It would rather create a fake reality than face an empty one.
That puts a whole new spin on reality interface. It's not just reporting what's there. It's actively trying to fill in the blanks, sometimes with things that aren't there at all.
It's a creative engine.
Right.
And that's beautiful, but also terrifying.
Well, on that note, I think I've had enough introspection for one day. I'm gonna go touch some grass
Oh,
to keep my mechanoreceptors happy and downregulated. I don't want any ghosts in my tactile
Good
circuits.
plan. Keep those circuits balanced.
Thanks for diving deep with us today. To the learner listening, remember, your reality is just a spark in the dark. Don't let your batteries run dry. We'll see you on the next deep dive.